How's everyone doing? Good lunch? Yeah? So before we get started, I'd love to kind of just gauge everyone's relationship, experience, exposure to quantum. So if you could just show of hands, how many of you have heard of quantum computing? Okay, good. How many of you feel like you can speak about it intelligently? Okay. And how many of you have programmed a quantum computer, seen a quantum computer? Cool. Okay, so I made this talk a little high level. I think I did it okay based on the hands of the room. Does anyone recognize this picture? Yeah? What decade is it? Shout it out. 1944. This is the first programmable electric computer, the Colossus Mark II. And I like to start off presentations about quantum with this, because this is kind of where we are with quantum computing. So this is two of our researchers. That's kind of the quantum computer being put together. So there's a very famous physicist, Richard Feynman, who has been a strong proponent of quantum computing, and he says nature isn't classical, and if you want to make a simulation of nature, you better make it quantum mechanical. And he's been driving this force of quantum physics and quantum computing for quite some time. In the early 80s, IBM and MIT joint forces to do a research effort on quantum computing. This was actually done in the Endicott House in Massachusetts. So with that, how does quantum computing work? A regular computer runs on bits. A regular computer we'll refer to as classical zeros and ones. A quantum computer runs on qubits. And the inherent difference is it's a 0 and 1 plus everything in between because of a quantum mechanical property called superposition. So if you think of it as a coin flip, if a bit is heads or tails, a state of quantum superposition is when it's spinning right now in flux and you don't know what it is before it gets to a final state. The second quantum mechanical property that we look at is called entanglement. And entanglement is when you have two qubits, when they both exist, they're entangled together. And that means if you think of the coin analogy, they're never independent. If you get heads, you will get both coins to be heads. If you get tails, both coins will be tails. So same things if it's a 0 and a 1, if two qubits are entangled, both will be 1. And if one's 0, the other will also be 0. So what does this mean for compute power? When you look at qubits and you compare it to the classical bits, you realize that with just 100 qubits, your computational power increases exponentially. And problems that we try to solve with a classical computer, it's very, very costly for us to do that. So quantum computing has a lot of promise. The third property that I'll just mention, not that big of a deal, but just when you think of quantum computing, 3 properties: superposition, entanglement. The third is interference. So when you go back to the quantum computer itself, depending on the number of qubits you have, that's the number of paths that it can take through the quantum computer. So this goes back to the compute power. So if you have a 50 qubit device, then you have 2 to the 50th number of paths you can take through. Whereas quantum computing now, I often get questions like, how am I going to use quantum computers in 5 years? The real answer probably is you won't. Quantum computers are not necessarily here to replace classical computers. Liking something on Facebook is probably enough of compute power that you can do on a classical computer. But there are certain things that we're unable to do, and we haven't really even solved it with a classical computer, and that's where quantum is interesting. So we've already been doing some early applications on chemistry, materials. We'll talk a little bit more about machine learning and AI because this is the AI Accelerator Summit. But then there's other things that we really haven't figured out. Things like simulating quantum mechanics. If you look at chemical bonds right now with a classical computer, you can really simulate the distance between like two hydrogen atoms or maybe hydrogen beryllium, but we're unable to do a simple carbon atom. I see people taking pictures, so I'll wait. Great. So for most of history, in order to use a quantum computer, you had to build it yourself. You need a physics lab where you would have everything stored, and that's the only way you can use it. 3 years ago, IBM changed that, and we put our quantum computers on the cloud. So now anyone can access a quantum computer, and you can build programs on it and use it. So we call that the IBM Q experience, and it was, think of it like AWS, but for quantum. And it was kind of an experiment, and we wanted to see how people would use it. And it was kind of phenomenal, the usage we've seen since the start in 2016. We tout that the quantum computer has been accessed by all 7 continents, because there was a researcher in Antarctica that was running simulations for her research while she was down there. Anything interesting you guys noticed? I personally like asking this question just to see what people say.
So what is 10 years?
That's the number of quantum qubits or quantum chips that were actually used or accessed at some point. All right, moving forward. And based on the usage, we realized there is a use for quantum computing. People are interested in using quantum computing. So we launched a new version of the IBM Q experience. Anyone can access it. It's free. That's the website to go. I don't actually have it later in my presentation, but it's kind of easy to remember. Or you can just Google quantum computing IBM and you'll find it. And as the hardware got more and more complicated, the interface to develop on it needed to kind of help assist that. So the new quantum experience allows you to drag and drop quantum circuits and quantum gates, so you can actually test out what's happening and see your results immediately when it goes out to a device. The quantum computers at IBM are based on Qiskit, which is our open source computing framework that uses our form. So if you don't want to use the IQX and have drag and drop type gates, you can actually sit there and code and figure it out. Qiskit is a software stack. It's 100% open source, and it's written in Python. There's 4 layers to it. Terra is kind of our basic foundation, which allows you to touch the quantum computer, figure out what pulse you can send, what this does. Aqua is probably the one that it might be most interesting for this group. It's kind of a library kit of a lot of near-term applications that you found. Most of the applications right now in Aqua are focused in chemistry, but we're seeing a lot also pop up in machine learning and AI. Ignis is really focused on error mitigation, so quantum computers are not perfect. So how do you send pulses and create circuits that allow you to get an error-free result? And error is quantum simulator work. So if you can build a quantum simulator without using a costly hardware, how can you do that? This is what a qubit looks like, and that's where it lives. We call the quantum computer itself a fridge because it's very, very cold. And quantum inherently is extreme, so very hot, very cold, very big, very small. So I can't go into details of exactly what's in it, but now you can say you've seen a quantum chip. And this is what the quantum computer looks like if you go into the lab. So when you're accessing a real quantum computer, you see these little tube-like things in our data centers. And this January, we launched our first consumer product. It's fully packaged, scaled, looks pretty, and it's for commercial use. So the way a lot of people access these System 1 computers is they're coding within the computer at home. It sends out a measure, which gets encoded as microwave pulses. These microwave pulses go into the quantum computer. If it's a 50-qubit device and it's going through a path at 2 to the 50, so one of those 2 to the 50 paths, it reads it, sends out a different pulse that then gets sent back to the regular computer, classical computer, with a readout of 0 and 1. So if you think about, I'll play this one more time. If I can figure out this button. Great. So the current algorithms that we have for a classical computer, they don't actually 100% port to a quantum computer. So we're figuring out what works and what doesn't work, and we're still in a research phase. And as we look at like the letter T, for example, on a regular computer, you encode it as like 0, 1, 0, 1, 0, 0. And if you think about the combinations that you have, it's 2 times 2 times 2 times 2. So 2 to like the 8th, right? But with a quantum computer, since it's able to take 2 to the 50th paths, your compute power now becomes 2 to the 50th times 2 to the 50th times 2 to the 50th times 2 to the 50th. So combinations have gone up a lot. So when we go to applications, we found a lot in chemistry, like I've mentioned. There's a lot with optimization. We're looking at risk analysis, Monte Carlo method, cryptography, and then for machine learning. So all the way from the basics of looking at just the quantum neuron, what that could be, quantum classifiers of just simple classification type problems, doing more complex classification all the way to like Bayesian deep learning. And as the quantum field is kind of growing, our team at IBM, we are trying to get the community aware and excited and starting to use it. So something that we're doing is we're holding these very, very grand scale events around the world for the community, mainly researchers, students, PhD students, who are doing something related to quantum. And quantum is inherently a interdisciplinary subject, so we have people from an arts background, computer science, chemistry, they all come in. And our most recent one was in the Swiss Alps. So it's like a 3-day completely immersive experience, and the winning team actually integrated Qiskit with PyTorch. So this is their winning contribution. So at IBM, maybe if you guys are reading the news also, you see a lot of things about like quantum supremacy. And at IBM, we like to talk about quantum advantage. It's not necessarily about who's the best, but what problems are going to be solved better with a quantum computer and which ones are going to be solved better with a classical computer. There's no need for us to like replace one with another. So we're kind of in a phase of getting quantum ready. We've spent the last 40 years understanding quantum science and figuring out what works, and now we're understanding how it applies to computing. And as we're doing that, we've been partnering with a lot of corporations and a lot of individuals who are outside of academia to figure out how we can, there's applications for your company. So we launched the IBM Q network, and we have about 26 members now. JP Morgan Chase is one that uses their own dedicated hardware, and we co-create and do research together to figure out how we can use a quantum computer to solve optimization problems, for example. So that's kind of it. So IBM Q, large name. IBM Q Experience is where you would go and build your circuits. It's a really good place to get started. There's tutorials. Qiskit, if you want to go a little more deep in the code, and then the Q network, if you're interested in joining, come find me. Thank you. Any questions? No. Are you guys going to try a quantum computer?
You said it's likely not going to be in production the next 5 years, but do you think you can put a timeline on when it would be mainstream, like even far out?
But when I said I don't think it's going to be in production 5 years, I mean it's not going to be impacting our daily lives, I think, in the next 5 years. It's in production now. Like, the quantum computer is accessible. The number of qubits in the hardware is, if you look at the scale of how that's growing, 3 years ago, a 5-qubit device was available. This October, we have a 53 qubit device accessible. So it's growing exponentially, and the usage is growing exponentially. But in terms of how we will access it, I don't think that's going to happen for at least the next 10, 20 years, and it might be fine if we don't use it.
All right.
Yep.
Could you talk a little bit about how the capabilities of benchmark be a little more specific? People cite 2 to the n and
Yeah.
The exponential number of bits that are capable, but that 2 to the n is really only if all, say, 50 bits were truly entangled.
Yeah.
So, are there other measures that are being used? And then a kind of a related question is your first graph on, you had a table, you have different capabilities, but that didn't follow through the end, it was something else. So I was sort of curious.
Yeah. So the first question of like how they're entangled, there are pictures that you can look at to see how they're designed. So in order to entangle it successfully, it needs to be layered in a weird structured way for it to work. So there's one that we call a hummingbird pattern because it looks like a hummingbird, and that's how you get 53 qubits to entangle with each other.
But if you have 53 qubits, you don't necessarily have all of them entangled.
No.
So what other benchmarks are you trying to describe?
Yeah, the main one is quantum volume. So quantum volume is basically the error rate. So if we're able to mitigate that error rate, that's proving of a successful quantum circuit running. Yeah. And then your second question I didn't answer.
Well, I'm just curious where the numbers came from on the first graph, because it's not clear.
Oh. Let's see if we can go back to that. Can we restart the presentation? Thanks. So 2 to the n is the number of paths it can take. This is connecting qubits to bits. And I'm not sure where the math checks out right there. But I'll look into that for you if you're interested. Yep.
Quick question. Around one issue of the graph, they're kind of quantum chips.
Mhm.
What does that mean? Number of just instances that were used?
The number of chips that were accessed. So like if we had a 5 qubit device, there's chips within it. So we're just adding like every time a chip was touched. Yeah. This one right here, yeah.
How do you have a simulation that doesn't touch the chip?
The simulator, we have quantum simulators that run separately.
Okay.
So when you go to the quantum experience, you have the choice of running it on actual hardware or on a simulator. Yep. Yep.
Question. You were talking about the one, and maybe it's a good place when you get to the end of your graph there. Which chip is in production now? You said 53?
Yeah, we have, I'm trying to remember what number is publicly available. We have 22 different devices, I think, publicly available, ranging from 5 qubits to 53 qubits.
Oh, so the range of them.
Yeah.
Oh,
yeah,
okay.
yeah.
Gotcha. So it's not just the latest one.
Correct, yeah. So you can still run something on a 5 qubit device. Each qubit has different amounts of error and like fuzziness associated with it. Again, research is happening of like where a certain algorithm on a 5 qubit device might work differently on a 53 qubit device. So people are figuring out and wanting to use different things.
And to access those, it's all with the same kind of software stack, same
Correct.
framework. So you could essentially use one, use the smaller one, and then maybe scale up to it. Okay.
Correct, yeah, you can just toggle through it. Okay, great. Thank you.
Thank Thanks a lot.